Hello everybody. This presentation is about the interpost PUF. It's a new design of a so-called silicon physical and clonable function that can be used for analog keys, to store analog keys, and it has many applications. Now, what we're going to talk about is a new design that is secure with respect to all state-of-the-art machine learning attacks, and I'm going to talk a little bit more about that in a moment. Now, all of this is done by a big team. We have Ha over here, Ha Nguyen. We have Durga, Shenglu, Khalil, Uli Roermeijer, and myself, Martin. So, what do I like to present here? As a team, we're going to present each of us a part of this presentation, and I will talk about the concept, the overview, the motivation, a little bit of the background to physical clonable functions. But really, after this, we're getting into the details. So we'll explain the core component to how you build a circuit-based or a so-called silicon PUF. And that is actually the so-called arbiter PUF, which can be extended into what we call the XOR arbiter PUF, meaning you have multiple arbiter PUFs that are whose responses are being combined in by using a XOR. And then we'll show how to use this concept to build our interpost PUF. Now, the rest of the presentation is all about analyzing the security, and in the end also about how to implement these on FPGA, and whether you can do that even in a proper way, and so forth. And we talk about the performance and so on. All right, so let's start with the concept, the overview, the motivation. Well, when we talk about a physical clonable function, the idea is that we want to bring in a challenge, just like a function takes in an input, you want to get out an output that we in this case call a response. Now, the hardware primitive that we like to develop is a special one called the physical clonable function, where we make use of process variation. So imagine if you're going to build a circuitry, then if you clock it, then we know that the same digital functionality will be created across different manufactured devices. On the other hand, if we would really look at the analog behavior in detail, then all these devices will react a little bit differently. So the manufacturer variations that create, say, this circuitry can be exploited, and this process variation that is inherent can then make these devices unique with respect to one another, even though they exhibit the exact same digital computation. Now, this can be exploited to create a hardware primitive that takes in a challenge and outputs a response. Both are digital, but how this is computed is really about exploiting these analog manufacturer variations that build the response in the end. Now, what are the applications? Now we have device identification that I just talked about, but you can also use it for authentication and crypto key generation. And there's a lot of literature around that as well. So let's have a look at where we are. In the PUF world, we have actually different kinds. The world that we call weak PUFs. And, you know, sort of instinctively, we want to think of a physical clonable function as having a certain input space that the challenges are taking from. And if that's a very small input space, we'll call it a weak PUF. Why? Because you can actually, well, it's actually possible to enumerate all the challenges if you have access to that PUF as an adversary, for example. And if you then wait long enough, because it's just a small number of challenges that you need to feed into the PUF, then you can get all the mappings from challenges to responses. And this we actually call challenge-response pair. So you have only a small number. Now a ring oscillator PUF is one of those, SRAM PUF, and so forth. On the other hand, if you have a strong PUF, we really have a large number of CRPs. Now, concretely, in physics, we are always bounded to a certain concrete number of CRPs, but instinctively we want to say there's a difference between these two classes, where the strong puff really has so many more CRPs that it does become hard and impractical to enumerate. Now, current puff designs, like these guys, well, what are the properties that we like for a physical clonable function? On one hand, we want to make sure that if you have a physical and clonable function that is manufactured by a manufacturer, so it is unique because of the manufacturer variations through which it got into being, then we want it to be very hard to be cloned, in the sense that I can create as the manufacturer or some other manufacturer an exact hardware copy. So that should be truly hard. Now, because you're working with manufacturing variations, the assumption is really we cannot do this. On the other hand, though, maybe it is possible to not make a clone in hardware, but possibly one in software. So, you know, we have a whole list of challenge response pairs, and maybe I can somehow find a beautiful underlying structure that I can sort of represent the table from challenge to responses in a very smart way. So somehow I'm able to model it, and that software model can now be used instead of the puff to impersonate and to perform a proper attack on wherever the puff is actually used in whatever crypto protocol it takes part of. So, besides the hardware unclonability, we also like software unclonability. And what we have seen so far is that machine learning actually is an ideal mechanism to figure out really reliable models so that we can impersonate the puff that we know today. So we have classical machine learning attacks. It is based on reliable CRPs, meaning that you know, it's not very you know, sensitive to measurement noise. And we have a whole bunch of methodologies that can help us to actually create a model for a puff. Support vector machines was one of the first ones to be used, logistic regression, the most powerful one, other kinds that have been studied in literature. Now, if you're looking at these challenge response pairs, when we generate those, well, there is some measurement noise. So some temperature variation, some voltage variations may actually cause the response bits to flip, even though we feed the puff with the exact same challenge. So let's say we are going to feed a specific challenge, C, 100 times. Well, I may measure a response that is, say, 90 times a 1 and 0 10 times. So clearly it's noisy. Sometimes it's not always giving you the exact same response bit as an output. So for those noisy CRPs, we can then figure out what the reliability is. So we will say, okay, 90% of the time we get the response bit 1 out. And it could be 95%, it could be 80%. But the point is that for that specific challenge, we see that there's a little bit of noise. Sometimes we will actually not measure it properly according to the majority vote of what we originally would like to see. So these noisy CRPs, if you measure these challenge response pairs multiple times for a fixed challenge, so you can figure it out, you get essentially challenge reliability pairs. And those can be used in Becker's attack. He got this really nice paper that showed that for CMA ES, evolution strategy, and you use these noisy CRPs or challenge reliability pairs, you can actually break all existing silicon or circuit-based puffs known to date. All the strong puffs that we have so far are actually based on exploiting silicon puffs, manufacturing variations in silicon. And after Becker's attack, we were left alone with essentially no secure strong puff. all of them were broken by machine learning. So what we want to do today in this presentation is to show you a new design, an interposed puff design, that will actually be, according to our analysis, secure against all the known classical machine learning attacks, and also the advanced machine learning attacks that are based on noises here piece, like Becker did. So that's pretty cool. So enumerating all of these designs, the arbiter puff, the XOR A puff, the feed-forward puff, and so forth, they are all broken according to these machine learning attacks. The nice thing about those silicon puffs, those designs, are that they're extremely lightweight. It's beautiful. There are other puffs over here that have been suggested, but there's no security proof whatsoever on those. Then there is very heavy designs that effectively exploit the interface around the puff. And if you include the logical interface that communicates with the puff itself to be part of the trusted computing base, then you can build something that we call an LPN puff. And essentially the LPN problem, the hardness of that underlying problem, is going to help you provide a security proof. But it's extremely heavyweight in the sense that the footprint, the trusted computing base, in the form of, not just the puff, but also that circuitry for the interface, is really a lot. So what do we want to do? We actually want to take that light